So section 3 talks about correlation. Specifically, we're talking about finding confidence intervals for slopes. So we're going to start out here. Just recall that y equals a plus bx is the sample base least squares line that we're talking about. So when we're finding the line of best fit, this is the equation that we're looking to find it with. And what that represents is a sample base, but we want to really know the population least squares line, and it's in theory. So this is the equation: y equals alpha plus beta x. So alpha is going to be your y-intercept, and beta is going to be your slope in this case. So the slope b, which is our sample base least squares line, is an unbiased estimator of the true slope beta, and the intercept a is an unbiased estimator of the true intercept alpha. So we really want to find confidence intervals for the regression slope. So if you remember confidence intervals, we've mainly been working with 90%, 95%, 99%. No matter what the percent is, we're looking for that level. So level C confidence interval for the slope B, the true regression line, is the sample slope plus or minus T star, which remember T star is your critical value, times the standard error of the least square slope B. Okay, you're not going to have to be able to calculate this. It'll be given to you in a problem, or you know, you can also solve this using your calculator. So you know, if we solve it using the calculator, it would be something that the calculator just finds out for you, basically. Okay. One thing we will need to know is the degrees of freedom. Our degrees of freedom are equal to the sample size minus 2, so n minus 2. So if we're looking at this problem here, it says good runners take more steps per second as they speed up. Here's some randomly gathered data. So we have 1, 2, 3, 4, 5, 6, 7. So that means if we're looking here at our degrees of freedom, it's going to be n minus 2. So that's going to be, in this problem, 7 minus 2, which means that our degrees of freedom are equal to 5. Okay. Our critical value, now your calculator can solve this for you. We also used a graph to be able to find this sum. If we're using our calculator, what you're going to go to here, you're also going to have it on. You want to hit second distribution. Now your screen is going to look different than this, mainly because the function that you need here is number 4. So your number 4 in your calculator should say 4 inverse t. Okay, when it says 4 inverse t, obviously you're going to choose 4, and it's going to ask you for the area and the degrees of freedom. We just found the area right here, or excuse me, the degrees of freedom right here is 5. Now in this problem below here, which is what we're going to solve with this data, it says find a 95% confidence interval. So we have to remember, when we find a confidence interval, it's finding that middle 95%, the values that are going to compact that middle 95%. So that means 5% is on the outside, but 5% is on both sides. So let's see how good I can do drawing this here. So there's our curve. We have this. These are going to be our two critical values. So this is the middle 95%. Okay. Well, our calculator wants to know what this area is right here. Okay. Well, if this is 95%, that means there's 5% combined between these two, which would mean that this area right here is equal, and that's really big text, to 2.5%. Okay, so that's what we actually want to enter in there. Okay, so if we're looking at, let's say, a 90% confidence interval, that means that there's 90% in here, 10% on the outside. So instead of 2.5%, this is going to just be 5%. Okay. So if you enter that in, you should be able to find your critical value, and I believe it's 2.57 or 2.58. I forget how the rounding is specifically, but it would then be plus or minus 2.58, because If you're once again looking at this equation here, we have plus or minus the critical value, so it would be our slope plus or minus our critical value. Okay, now we also need to find our equation here, so we're going to end up finding a and b. Now remember, for a sample, your equation is y equals a plus bx. So if we go back to the calculator here, looks like I shut the calculator down by accident. Okay, so we go back into the calculator here. We need to enter our data in. So we go to Stat, Edit, and we enter it in. So we go 15.86, 16.88, 17.5, 18.62, 19.97, 21.06, 22.11. Okay, so that's our first list. Our second list is our steps. So we got 3.05, 3.12, 3.17, 3.25, 3.36, 3.46, and 3.55. Okay, so there we have all our information in. Now remember, we go to Stat, we go over to Calc, we come down here to number 8, which is linear regression a plus bx. Okay, and here should say x list, y list, so you should enter in your speed for your x list and your steps per second for your y list. Remember, your x list is always your explanatory variable, y list is always your response variable. So we hit it here, it gives us a and b. Yours should give you r squared and r. So a is 1.77, b is about 0.08. So here we would have 1.77 and we have 0.08. Okay. So if I would write out my equation here, it would be y equals 1.77 plus 0.08x. Okay, I can plug in any value for x for the speed, and it would give me y, which would be my steps per second. Okay, so the interpreter slope, we'd have 0.08. So 0.08 in this problem is telling us that for every additional foot per second, we would take an additional 0.08 steps per second. Okay, so that's what our slope is telling us in this problem here. So now we want to find a 95% confidence interval for the true slope. Okay, so you can see that's what it says right here. What you do is you go to Stats, Test, Linear Regression, TInt. Now once again, my calculator doesn't have this, so you need to make sure you're using TI-84 to do this. But we'll just go to it together, where I'll show you where it would be on the calculator. You go over the tests. I usually hit up because it's the second one from the bottom. It's going to be in between these two on your calculator. Okay, my calculator doesn't exactly have it, obviously. So when you go there, you'll be prompted through this all. It's going to say regular EQ. What that is asking for at the bottom is where do you want the calculator to store the regression equation. You can leave it blank, or you could store the equation in Y1. To store it in Y1, you do the following. You hit vars, y-vars, function, Y1. You don't have to. You can just leave it blank if you want, but if you do that, it's going to store it in here, your y equals, so then it could be graphed. Okay, so if you're going to enter this all in, then it's going to ask for an x list, it's going to ask for the y list. Okay, you go through, and it should give you your confidence interval. So just pause this video for a second, go through the process, and find your confidence interval. So once you find your confidence interval, what you should have found is 0.076. It should be about point. I don't know why it's typing so small. 0.076 to 0.084. So let me increase that a little bit here. Okay, that's a little better. Okay, so you should find 0.076 to 0.084. Now that's rounded off a little bit. Just be careful because I've had people rounding it to 0.08 to 0.08. It's not a good way to round. Obviously, I can't see the difference in the values. So yeah, I teach you the round sum, but you need to make sure that we're rounding appropriately here, so that I can see that there's a difference here. So 0.076 to 0.084. So what is that telling us in this problem? That is telling us that we are 95% confident that for every additional foot per second in speed, there will be an additional, there will be between an additional 0.076 to 0.084 steps per second. Okay. Once again, we always have to remember when we're doing these problems that this is not telling us causation, it's telling us a correlation. So based on the data that we have, we can show that there's a correlation between the two pieces. Okay. So let's continue looking here. So I mean that's the basics with confidence intervals. Now there's going to be times where we're not going to be able to use the calculator. For instance, here we do have a data set, so it's nice and easy, but there are actually going to be times where we have to use this equation. So if we're going to, and this is a good example of it here, so if we look at this example here, we have infants who cry easily may be more easily stimulated than others, and this may be a sign of higher IQ. The following is Minitab regression output for the data. Assume there are 38 data points. Construct a 90% confidence interval for the true slope. Assume all conditions for inference are satisfied. Okay, that confidence interval that we find here, remember we're finding the confidence interval for the population slope here, so that 0.076 to 0.084, we can say that we'd be 95% confident that our true slope, or the true amount of additional steps that will be taken for every foot per second, is between those variables. But this is a program called Minitab. It's a statistical program that can be used to analyze data, and it's one of many, but it's one of the more popular versions. So this would be an example output from this program. So here you can see the regression analysis. The regression equation is IQ. So the baby's IQ is equal to 91.3 plus 1.49 times the cry count. So how many times they cried in that specified amount of time. Okay. So remember, 91.3 here is going to be your y-intercept. So literally interpreting your y-intercept would be saying that for 0 to, if our cry count is equal to 0, the baby's IQ would be 91.3 in regards to this equation. Okay, so this best fit line, this least squares regression line, it would be saying that 91.3 would be, if I were to predict what the IQ of the baby would be based on this least squares regression line, it's going to be 91.3. 1.49 is your slope, so it's saying for every additional time the baby cries, you would be predicting that the IQ would be 1.49 points higher. Okay? Remember, once again, this is purely correlation. This is not causation. So don't go pinching babies thinking that they're getting smarter because they're crying or anything. Okay? So these are different values here. Now we have this equation here to solve for our confidence interval. But we need to know what our slope is. We just found that it's 1.49. Our critical values, we know how to find that. Okay? And our standard error of the slope of the regression line. Okay, so right here, that's given to us in this problem, it's 0.487. We also have here r squared is equal to 20.7. So r squared is we